Okay, we are live on YouTube. There is random person watching our YouTube videos, all of them, not just your class. So whatever I guess, I don't know how would anyone use like our lectures because it is heavily focused on the students in this university, but I guess they can.
University of Alabama aerospace program, like randomly watching.
I guess that's a compliment to my lectures in a weird way, but I appreciate it though. Okay, so let's, the last thing we talked about in, what do you have against University of Alabama? It's a good school. Where the last thing we talked about was the wave drag, right? That's where we stopped. Okay, so today we are going to finish chapter 5 and we are going to solve some example problems and start chapter 6, which is going to be the start of your airplane performance, the meat of the flight mechanics part of the class. When we are dealing with chapter 6, I will provide some handouts for you. So chapter 6 of the book will not be the only reference when it comes to flight mechanics and the aircraft performance in general. And you will be questions on those handouts. Blackboard, okay. You guys couldn't hear him, but he's talking. So I created another live stream on YouTube. You want to refresh it, so it should be another one, a new one. Sorry, guys. Technical difficulties. Why doesn't Blackboard have any videos? Okay, that. No, okay. See, I'm moving away from GoPro because it is very, software on GoPro is very shaky. So I'm gonna use a dedicated webcam. See, it just stopped working. GoPro stopped working. Same thing happened yesterday. Just stopped working. Did you find the YouTube? Yeah, okay. Pardon me? It was not made to be a webcam, so they tweaked it a little bit. So I guess you guys found the YouTube live stream. Okay. Pardon me?
You wear a headband where there's like a POV with the GoPro.
Yeah. Okay. I lost it. There were we. Okay, so we are going to finish chapter 5 today. That's the idea. We are going to do the start chapters, just a little bit of chapter 6. If we had enough time, we will solve some example problems in chapter 5. And then that will be it for today. Your homework will also be posted next Tuesday. There is a wellness holiday for you guys on, I think it is Tuesday, February 29th. It is on your on the syllabus, on the class schedule, course schedule. What I'm gonna do is probably I'm gonna record a lecture and post it for you, right? But if you guys are against that idea, it has to be a unanimous agreement, right? If you guys are against that idea, I won't do it. I will just do a face-to-face class. Okay, what do you guys think? Okay. Then I won't post the lecture. Okay, so let's begin. So far, we have learned about the friction drag, the pressure drag, or what's called the form drag, and the wave drag. The combination of all of these together is going to be called the profile drag. or total drag on your wing. Of course, the wave drag only comes into play when you're dealing with transonic or supersonic flows. Okay. So whenever you were asked to calculate the profile drag of a wing, you have to, the first thing you need to do is to determine whether it's supersonic, transonic, right? If it was subsonic, then this part goes to 0, and you have to calculate pressure drag and friction drag based on the equations you have seen so far. That was the last part remaining from the wave drag that we needed to talk about, from the profile drag that we needed to talk about, I mean, the next part is going to be moving on from two-dimensional airfoils to wings. What is the main difference between a wing and a two-dimensional airfoil when it comes to its geometry and shape? It is not infinite. I think we talked about this as well, right? So two-dimensional airfoil, we are going to assume it is an infinite wing. What does it mean? It means that all of the effects in these directions are going to be neglected. And this is what the first generation of NASA engineers did when they were trying to characterize different airfoils and different like flight properties on a wing in their wind tunnel. And this is what most people do when they want to characterize a specific thing, right? But when you're dealing with a wing, we are dealing with definitely a finite wing. With a span and airfoil. So this airfoil, the shape of the airfoil, the chord, and all of these things can change, right? If you're dealing with a regular wing with a constant chord, then we are dealing with a rectangular wing. Just the first generation of wings that were produced were rectangular wings. Okay. Rectangular wings. One thing, the first thing you have to deal with when you come to wings is the aspect ratio of the wing. The question is, what is aspect ratio? That's the first question you need to answer. This is my question for you guys. What is aspect ratio?
Does it have anything to do with like the aspect ratio of monitors? You know, like a 4:1.
It's essentially the same thing. It's the same thing. So how would you apply that concept here to a wing?
4 times as long as it is.
Okay, if the aspect ratio is 4, it's 4 times this is width, right? This is not, this one is length. So this is like, if the aspect ratio of a wing is 4, then it's 4 times wider than its line. I mean, width and length and depth can be a little confusing, but you get the idea. So if the aspect ratio of a wing is 4, it essentially means that the span is 4 times the chord length, okay, for a rectangular wing. What if we are not dealing with a rectangular wing? So essentially, we define the aspect ratio as B, the span length, divided by your chord length. But what if the chord length is changing? What should we do? How can we calculate the aspect ratio? One way is to take the mean chord length, right? Math, AMC, which was the integral of all of the things. But for that, you have to have the C as a function of Y. You have to have this function to be able to integrate and take the mean chord, right? What else can we do? I think you should have seen this in your aerodynamics, right?
We split it into different portions.
To calculate the aspect, how would you calculate aspect ratio then?
Calculate each section and then average all your aspect ratios together.
But okay, let's say you're dealing with this type of wing, and this is a top view. It doesn't really matter if you break it into different portions. Your coordinate is still changing, and you don't have the function of that change. Okay?
I would say the best way to do it would be
Integral. Okay. But it is not the most practical way to do it, because a lot of times you don't have this formula, this function, C of y, right? So we can change our approach to this, right? Instead of defining it as B divided by C, we can bring in the area. What would be the area of this rectangular wing? B multiplied by C, right? So let's multiply the numerator and denominator by, or let's call it S, surface area. Multiply both by B, and then you're going to get the same thing for a rectangular wing, and this is something you can apply in other wings, right? As long as you have the surface area, you have the span, you should be able to calculate the aspect ratio of a wing. Okay. So, but what happens physically? The idea was that when you move from airfoils to wings, you are moving from an infinite wing in which you neglected the three-dimensional effects in the other direction, in the Z direction, for example, versus the finite wing in which you cannot neglect the three-dimensional effects. What are those three-dimensional effects or in Z direction effects that we cannot neglect? And we talked about it very briefly in the previous lecture, I think, as far as I remember. The downwash, right? We talked about it, right? Sorry. I just mentioned it, I guess. Something like that. Okay. So what does downwash mean? Let's have a front view of the string. Let's say this is your plane, a very rudimentary plane. And let's see what downwash is. The idea is, if you have, in order to generate lift, you have to have higher pressure distribution on the bottom, on the lower side of the wing, right? And then it will push the wing upwards, right? That will be your lift, upward lift, right? Which is going to be true. There won't be any problem with it as long as you are dealing with an infinite wing, right? But when you are dealing with a finite wing, you are introducing these tips to your wing, right? And what's going to happen is that here, you will have, see, GoPro just turned itself off for no reason. Okay. Pardon me? Yeah, I didn't want to learn about that one. Exactly. So what is going to happen at this tip? We have high pressure, low pressure. You will have, exactly, flow is going to move on the upper surface of the wing. It's going to happen in both directions. So you are going to lose some of the pressure differential. The pressure on the lower surface is going to decrease. The pressure on the upper surface is going to increase, right? And we have seen this in aerodynamics. You have analyzed it. You have seen the theories and all of those things, hopefully. So you know how to deal with this. And then because of this movement of air, you will see wing tip vortices that are going to leave the wing, right? But what is the effect of this when it comes to lift coefficient and drag? Because of this fact that, let's look at a velocity direction. Let's say this is the infinity and this is your wing. Because of flow leaking to the upper surface, you will have a component of velocity in this direction, right? Does it make sense? Which means that your flow vector, your flow velocity vector, is going to be tilted a little bit. So this is going to be the vector, the velocity vector, your wings is, right? The real velocity vector, the flight velocity vector, is the infinity vector, right? It is the direction. But the velocity your wings is going to be in this direction. What does it mean for the angle of attack? Look at this airfoil. Right? This is going to be your angle of attack, right? Alpha. What does this mean for the angle of attack, the new angle of attack? My drawing is very messed up, but as you can see, I mean, I don't know, you cannot see that here, but hopefully you can imagine that we are losing some angle of attack, essentially. Does it make sense? Let me draw this again. What is the angle of attack here? Is this, right? What is this angle? Is it smaller than this or bigger? Smaller. The new direction of your flow is going to be tilted down a little bit, right? So the angle you're going to see, which I cannot show here very well, is going to be, maybe I shouldn't. That's the idea, right? You get the idea? Do you get the idea? So the angle we're going to see here is going to be tilted a little bit in the direction of the core. That's the idea. So you're going to lose some angle of attack. Okay, so what does it mean? When you're losing some angle of attack, you're essentially losing some lift, right? Yes.
It's like right on the verge of being a slow condition, where the aircraft is angled upwards, but still traveling at a level of flight.
How would you make that connection though? How is this similar to the slow condition?
Because I'm just imagining it's like normally if you have an alpha of an angle attack positive, the aircraft is climbing, but you could be moving at a slow enough airspeed.
No. A positive angle of attack doesn't generally mean you're climbing. It really depends on the lift you're generating. Not because of this, in general. Let's say you're dealing with an infinite wing, you have a positive angle of attack, you're changing the value of lift. If the lift you're generating is equals to weight, then you will have a cruise condition, right? If it's higher than weight, then you will be climbing. If it's lower than weight, then you will be descending, okay? So do you want to elaborate on your first question then, or is it solved now?
I guess I was just trying to figure out if whenever this happens, is that akin to a cruise condition?
Not necessarily, but
Or is it cruise condition?
I cannot make the connection. That's why I don't know how to answer your question. I don't know how you are making the connection there. So a cruise condition, right, doesn't have anything to do with the angle of attack. Cruise condition has things to do with the force balance. If lift is equal to weight, and we're going to see that actually in the equation of motions that we are going to, then you will have cruise condition, right? But the thing is, if you come back to CL versus alpha, right, you may need to be able to get the cruise condition. You may need to generate this much lift, right? Or for a lighter aircraft, you may need to generate this much lift, right? Which are you can change the angle of attack to get the cruise condition, right? Okay. But this is not something you do. This is something that's happening because of the design, like the aspect ratio higher. I assume we are talking about the effect of aspect ratio here in a minute. But you have designed something because of this pressure leakage that is out of your hand, right? Because you're flying, right? You cannot change shape of the, I mean, you can, but you cannot change your design, can you? In the middle of flight, man. So this is something that's happening because of the physics. It is not like the angle of attack that you can. I don't know if it was clear or not. And I still cannot make the connection. But yeah. So cruise condition is different from this. Assault condition is a little different from this as well. These are three separate phenomena. There may be similarities, but I don't see the similarities. So of course, all of them are dealing with angles of attack and the lift coefficient and all of those things, but okay. Where are we? So the angle of attack, we are gonna get a reduced angle of attack. What does it mean? It essentially means that the lift you are generating is going to be in a different angle than the lift you are supposed to generate. So lift has to be normal to the flight path, right? But because on the wing, you are going to get a different angle of attack, your lift is going to be tilted a little bit as well, which means that it will produce a force in this direction, in the tangent to the flight path direction, right? Which is called the induced drag, because this drag is induced by the lift. And the difference between the real angle of attack and the effective angle of attack, you're going to see it's an angle itself. It's called the induced angle, induced drag angle, or induced angle. And what is the relationship between lift and drag coefficient? Can we find a geometric relationship between lift and not the drag coefficient, the induced drag? It is tilted with the induced angle, right? So what is the direction? What is the relationship between lift and no, what is the formula? How can you relate? This is going to be your lift. This is going to be the lift and drag because of this induced angle of attack. This is alpha I, right? Li, di. This, we want to find this based on this. It's just a geometric relationship, right? A sine and cosine relationship. So what is the relationship? Your L, your di is actually going to be L sine of alpha I. And since we are dealing with lower speed flights, what's going to happen is that sine of alpha I is going to be very close to alpha I. So di is going to be L alpha I. Okay. That's the idea. We are dealing with low angles of attack. Your alpha I is going to be so small. So sine of alpha I is going to be equal to alpha I. But alpha I itself, from your aerodynamics, and if you don't remember how you got there, I'm pretty sure you can go back. Hopefully you have covered this part, but if not, the derivations is not important here, just the final formula. Alpha I itself is a function of lift coefficient and the aspect ratio. Okay. Do we remember this? Okay, you have hope. Yeah. So based on this, your induced drag is going to be equals to lift multiplied by lift coefficient pi over alpha r. And if you divide everything by Q infinity multiplied by the span area, you're going to get Q infinity S di L over Q infinity S multiplied by CL over pi AR. Okay, what is this? Di over Q infinity S. That's di. Di divided by Q. What was the definition of a force coefficient? Exactly, induced drag coefficient. So we're going to get CDI. And this is the definition of the lift coefficient. We can bring the lift coefficient into here. So your induced drag is going to be CL squared over pi AR. So as you increase the lift coefficient, your drag coefficient is going to be, your induced drag coefficient is going to be increased as well. Something that you have to keep in mind is this was derived for an elliptical wing. You remember elliptical wings, right? And their importance. Okay, so if we include a correction factor, if we are dealing with non-elliptical wings, it's going to be CL squared pi EAR. And that E is the wing coefficient, correction coefficient, that goes between 0 and 1, 1 being the highest, which is the thing you're going to get on the elliptical wings, which is going to be giving you the lowest induced drag coefficient. Okay.
Is E a value given?
Yes, you don't need to calculate it. But you can actually go back to the airfoil theories, the wing theories you had in the previous class, and find the lift distribution over the wing, right? Based on the circulations and all of those stuff. Find E based on the comparisons of those lift distribution over an elliptical wing and a regular non-elliptical wing. So you should be able to do that, but you didn't do it in aerodynamics, you are not going to do it here. Okay, so let's talk about the importance of aspect ratio here, or the effects of aspect ratio. What is going to happen if you increase or decrease aspect ratio? What is going to happen to your induced drag? If you increase the aspect ratio, your induced drag is going to decrease, right? Why does that happen? How can you explain the physical phenomena that is behind this decrease in the induced drag because of increase in aspect ratio? Look at that wing. What is going to happen if you increase the aspect ratio? Exactly. So your wing is going to become wider, right? And because of that, the flow that is leaking from the bottom surface to the upper surface, the lower surface to the upper surface, is going to be, it is not going to be negligible, but it's going to be less dominant. Okay, so that makes sense. And yes.
Is this the same reason that gliders have really, really long thin wings?
That's definitely one of the purposes, because you want to reduce the induced drag. But what I would assume, when they were first designing the glider, they had no idea about the induced drag, right? So I don't know the history exactly, but one of the main reasons they do the aspect ratio, the high aspect ratio wings, for gliders is the stability, right? It can be more stable. And in general, your higher aspect ratio thing, you are covering higher air, right? Higher surface area of the air without increasing weight that much. So you'll be generating more lift. Okay. How can we? No, let's forget about that. It is a discussion by itself. But I think you have had a discussion on the effects of aspect ratio on stability, right? In your aerodynamics. Yes? Okay, what is the effect of aspect ratio and stability then? In 101. Mm-hmm. Okay. So you have so you know about this. You have already talked about it. So the downwash phenomenon and the induced drag, which means that your total drag on a wing is going to be equal to your induced drag, your profile drag, which is going to be like CD naught plus your induced drag. Let's actually do this CD and do this CD total, right, for now. So total drag coefficient is going to be CD, your profile drag, plus the induced drag. And the profile drag is the drag you are going to face because of the geometry of the aircraft. So you can calculate that profile drag when your lift is 0, right? At like negative angle of attack. So what does it mean? It means that when you come to a drag polar formula, which you have seen a drag polar, you have actually drawn a drag polar, and you know, I haven't looked at your drag polars. I don't know if they were correct or not, but I guess I have to talk to Saurabh about this. But you know that it doesn't start from 0. So for 0 drag, you are not gonna get, for 0 lift, you are not gonna get 0 drag, which essentially talks about the fact that there is a profile drag that is there because of this. Okay. So the idea here is that you are going to get your minimum drag, CD mean, at this location. Why? Because this induced drag is always positive or 0, right? There's no negative induced drag. So when this 0, you're going to get a total positive drag coefficient. But this doesn't always happen. Or let me put it another way. This never happens. Yeah. Your drag polar, your minimum drag location, is slightly shifted in this direction. For most aircrafts, not all of them, for most aircrafts. So minimum CD mean is going to happen at a positive lift value, which doesn't make any sense based on that equation, right? Why do you think that happens? Let's think about it a little bit. Okay, you're getting warmer. How would you relate that to angle of attack? Theory-wise.
And like you said, the has to balance out with the weight.
No, you started in the correct path, then you got colder. We are not talking about level flights here at all, right? Level flight, again, cruise, takeoff, landing goes back to the force balance. We are not talking about any force balances here. This is a relationship between lift and drag, right? We are not writing a balance between lift and drag. It's just a relationship between the two. How can you calculate drag from lift? What is the relationship between the two? Okay. So don't get bogged down with the force. Yes. CL. CLCD. Lift go. This is a drag polar. So C of L versus CD. If you haven't seen this before, drag polar. It can be actually presented in the other direction. So you can have CD on the x-axis, CL on the y-axis. It doesn't really matter. But yeah, who else? I want you to jump in and talk about this, all of you. So at this point, we already know that it is somehow related to angle of attack. Right, the explanation here. No, no. So let's think about it this way. Where in most airfoils, non-symmetric airfoils, cambered airfoils, where do you get the zero lift coefficient? At which angle of attack do you get the zero lift coefficient? A negative value, right? So it is a negative value of angle of attack. What does it mean? It means that your airfoil is going to look like this. Okay. So when you have this type of airfoil, you will get a very high flow separation here because of this camber, and your profile drag is actually going to increase. So although at this point we don't really have any induced drag, but your profile drag is not constant anymore. It's going to increase. Okay? Or the changes of profile drag are going to be noticeable. That's the idea, compared to the changes in positive angle of attack, right? In changes in positive angle of attack, changes in profile drag is not going to be noticeable compared to the effects of induced angle of attack, okay? So it's going to move slightly. So the minimum value is going to happen somewhere else, mostly around the zero angle of attack, around that ballpark. But what is going to happen to this drag polar when you're dealing with a symmetric airfoil? What is the most important feature of a symmetric airfoil? Okay, how much? So what's going to happen to this figure, CL versus alpha, when you're dealing with a symmetric angle of attack, symmetric airfoil? It is going to start from zero, right? So you're going to get zero lift at zero angle of attack. So when that happens, you're not going to get any negative values, right? So you're not going to get higher profile drag at zero lift, right? So this is actually going to move back to the center. Okay, that's the idea. But the next thing we wanna talk about when you are talking about the downwash is the lift slope. What is lift slope? You haven't seen it in your aerodynamics? I'm going to give you some time to think. But these are the things that you have to, these are the things you may use actually in a real aircraft design, and you have to know them, right? What is a lift slope? Just think about it. It is a slope of a line that is related to lift. That's it. So this is this slope here. Lift slope is this slope, right? The slope of CL versus alpha line, right? When it's linear, right? We are dealing with the linear regions, right? So before the sol, essentially, your lift slope is going to be dCl versus d alpha. Okay. So CL versus alpha, we are going to, let's say, this is the thing you get for an infinite wing. Infinite wing, meaning that we are dealing with an airfoil. And this slope, so dCl, the alpha, we are going to call A naught. Okay. We want to see how much this slope, this is a theoretical slope, right? The infinite wings are not real. How much this slope is going to change or is it going to change at all when you move your analysis from an infinite wing to a finite wing? Okay. How much is it going to change? Okay, so we have one vote for the slope not changing at all. So what you're saying is that we will see something like this, right? This is what you're saying. Okay, so the slope of the linear region or the lifted slope is not going to change. Okay, what else? Shift left. So like this. Okay, we have one vote for. So the slope is not going to change because you're just saying that the shift is going to shift left. Let me actually, let me, how many colors do we have? Let me bring all of the options and then. So one option, the stall condition is a stall is going to happen at a smaller angle of attack, right? That's one option. The other option is that the zero lift angle of attack is going to be a smaller, right? It's going to be more negative. That's what happens when the thing shifts left, right? The zero lift angle of attack is the thing is changing. This is zero lift angle of attack, if you recall from your aerodynamics. Okay, what else? Tray. So we have 2 votes for Trey's idea. So let me put it this way. The correct idea will get 2 bonus points. Whoever votes for the correct idea will get 2 bonus points. I don't know. What part? Can you repeat that? I'm happy when you. What happens? I'm happy. I'm asking what happens when you move from an infinite wing or an airfoil to a finite wing. So when you include the effects of the downwash or the induced drag, what will happen to this lift slope and this figure in general? Its slope will increase. So you are saying we will see something like this, right? Okay, so we have 3 different opinions and 2 votes here. 2 votes. Okay, we have 3 more people who have to jump in. Not 3. How do we? Yes. You actually already you have 2 more people to jump in. Yes. Okay, 2 votes here. Let's make that 3. Okay. Yeah.
For the CL, the formula is lift over Q over S, and if your surface area is longer infinite, I'm going to make it just higher slope.
Okay, that is a mistake you're making, right? The surface area is not going to be infinite. Infinite wings means that we are neglecting three-dimensional parameters, but the surface area is chord multiplied by a unit length. So you cannot really analyze things based on that analysis, because you can have a wing, a finite wing that is chord multiplied by unit length, like b equals to 1, right? That can be a wing, right? So you cannot make that analysis based on surface area. Okay, so you are going to change your opinion. Okay. What about the zero lift angle? Is it going to start from? Okay. Okay, so I think at this point we are set for the opinions. We have 3 votes here, 2 votes here, and 1 vote here. And Nicholas got it. At the last minute. 2 bonus points. 2 bonus points. Okay, so but why does that happen though? First, yeah. Go ahead, go ahead. Okay, you're essentially, it is better to have a look at it from the other, like from other way around. Okay, let's go at, let's look at the zero lift first. When you have zero lift, you are gonna have zero induced drag, right? And lift, it doesn't, zero induced angle of attack, everything zero. So this is not going to change. Zero lift angle, that's for sure. But let's say you get here at this specific angle of attack, alpha 1, right? For alpha 1, the theoretical infinite wing lift coefficient is going to be higher. That was the idea. You are going to lose some lift to the drag, right? You're going to, like, some projection of the lift is going to contribute to the drag. So you're going to get a smaller lift coefficient, right? So your slope is going to decrease. That's the idea. It will also affect your stall condition a little bit. Your stall is going to most likely happen later, but we will talk about that in, we won't actually talk about it. It's going to not going to be a topic of discussion. So, but then the question is, how can we find the real slope, lift slope? Because in a wind tunnel, you most likely are characterizing a 2-dimensional airfoil, right? But in the real world, you want to find the relationship between lift and angle of attack for a finite wing. It is not that hard to like derive this formula, but I'm just going to write it down for you. Your new lift, the slope, this slope for the finite wing is going to be A. So a finite wing. Your new lift, lift slope is going to be equals to A naught, which was your 2-dimensional or infinite wing. A lift slope, 1 plus 57.3 A naught divided by pi E1 AR. Okay. So this is going to be the relationship between the 2 lift slopes. Something that you have to keep in mind is that here we are dealing with the angles has to be radians. Just want to make sure. Has to be in the gradients, actually, sorry. If you are dealing with radians, the angles, not the slope. But you have to represent the angles in gradients, like 2 degrees, 3 degrees, 4 degrees, 5, whatever, right? If you are dealing with radians, like pi, 2 pi, whatever, then that 57.3 is going to drop out. You have to drop that. So the relationship between the 2 lift slope. Is there any questions here? Okay. So this will be it for the discussion on chapter 5. there is one section remains. That's the swept wing analysis. I think we have talked about this swept wing. We have talked about swept wings in your aerospace lab course. You should have had a small discussion in your aerodynamics as well. But you will get a homework assignment that will be on swept wing. Essentially, I'm going to ask you to explain two things. One, how lift is generated, which is going to be section 5.19 of the book. You don't need to read that section. You can just read whatever. Just explain how lift is generated, what are the different perspectives. And the other one is going to be to explain the swept. What are swept wings? What are the benefits? What are the not good parts of those, and so on and so forth. Okay. But I will post this homework, so you don't need to do it on your own. I will post the questions. Just be aware. Okay, so we are going to move on to chapter 6 now. A very small part of that, just an introduction to chapter 6, essentially, which is very related to the discussions of the induced drag. I think it looks very similar. And then we are going to move forward. So for chapter 6, we are dealing with the aircraft performance. So we are moving up from wings, right? Elements of aircraft performance, and then we will talk a little bit about the stability. You will learn more about the stability in different directions in your flight dynamics and control, which you will take in a year, I guess, spring 2022. Okay, so we will have a small discussion on stability. It will be mostly stability in only one direction, but you will get the idea. But chapter 6 is going to be elements of aircraft performance. So we are moving up from wings and airfoils to aircrafts. The first thing you want to talk about is how to find the total drag coefficient. The total drag coefficient is a combination of something called the parasitic drag, CD and E, plus your induced drag, CL squared pi ER. What is the difference between this parasitic drag and the profile drag? Profile drag was specific to wings, but parasitic drag is essentially the drag that is there because of their fuselage, because of your wing, because of landing gear, whatever that may be generating drag. That is where all of them are included in the parasitic drag. Parasitic drag itself is actually a function of your lift as well, and the profile drag. So we can write this equation for it. Parasitic drag is essentially a function of your profile drag plus R, which is an empirical constant, plus CL squared. We can combine these two equations to give us an equation that is very similar to the profile drag equation we have seen before. So your total CD on aircraft is going to be CD and naught, which is the drag coefficient. Then your lift is 0. So to calculate this CD and naught, your lift has to be 0 plus. Then we are going to combine these two. We are going to combine this R constant and E constant and bring them all together. CL squared over pi ER. And this E here is going to be different from the E we have here. In this E, we have included the effects of R as well. So, but it is still the same constant, changes between 0 and 1, and so on and so forth. Okay. So this is the first thing you need to know about aircraft performance, how to deal with drag. And drag of an aircraft is always a function of its lift. Okay. We talked about the drag polars. And something that we need to mention. Okay, we talked about the fact that this minimum here doesn't really happen at 0 lift. It happens somewhere here. So if this is the case, then your equation is going to be different a little bit. You are going to get CD is equal to CD and minimum plus CL minus CL with minimum drag. So the CL that is happening here is squared plus pi EAR. So if the minimum drag doesn't happen at 0 lift, then you have to move it a little. You have to use this equation. Is there any questions? So for the rest of this chapter, we are going to deal with equations of motions from two different perspectives, from 0 acceleration perspective and a finite acceleration perspective, which is we are going to start working on those from next lecture. But as a, let's say as introduction part to the equation of motion, let's think about equations of motions. How can you derive the equations of motion for an aircraft? Equations of motions is everything in flight mechanics. As long as you can find the equations of motions, you should be able to find whatever you're looking for, right? So how can we find the equations of motion? CL, okay. Actually, that's CL at minimum drags. So this CL, this one. In this case, this CL at minimum drag is 0, so we don't really include it. How can you find the equations of motion for an aircraft? So the first thing you want to do is to find the coordinate system, like apply, okay?
I guess you want to compare thrust and drag and then lift and weight.
So write a force balance, right? So that will essentially give you your equations of motion. Write the force balance in each direction. And then use this Newton's second law, right? If the acceleration is 0, then the force balance has sigma F is 0. If it's not 0, then sigma F is equals to ma. So this will be the focus for the next lectures. But today, for the rest of today, we are going to, and this is a quiz, a pop quiz, an attendance pop quiz. I'm going to ask you to solve this problem for me. Yeah, if you could pass the paper to Nicholas. Appreciate it. So, this is the question. Consider a flat plate at an angle of attack of 2 degrees in a Mach 2.2 airflow. Does anyone know what is the significance of Mach 2.2? It is supersonic, but what is the significance of this specific number?
Well, it's a Delta column. No, it's not. Delta column.
Do you know what Concorde is? Pretty sure you do. The supersonic commerce. It is the cruise speed of Concorde, 2.2, exactly. So the length of the plate in the flow direction is 202 feet. So we have a flat plate, Mach 2.2, which is the cruise speed of Concorde. Alpha is 2 degrees. Flat plate is 202 feet, which is the length of the Concorde. Okay. Assume the free stream conditions correspond to a standard altitude of 50,000 feet. So free stream condition, rho infinity, P infinity, whatever, all of those correspond to the standard altitude of 50,000 feet. Okay, how would we define density and all of those parameters based on the standard altitude? From the table, right? Just go back to the table. I'm going to give you those numbers as long as you know that you have to find them from a table at the end of the book. You should be fine. And we want to find the total drag on this plate. What are the drags that are present here? All of them are present. Okay. But we don't have any mention of flow separation. So you can essentially remove the form drag. Okay. Friction and wave drag. Right? Form drag is the pressure drag. So you have to only calculate the friction drag and the wave drag. But the equations we have had for friction drag was developed for subsonic flow. So what should we do then? We have to apply a correction. And the correction is that you will have, there will be 20% difference. So the friction, okay, let me actually ask you. What do you think is going to happen to friction drag as we move to supersonic? Why? More That's the feeling I always have. Why? You have to elaborate. So you're like a thicker bound layer? Yes. So you're saying a thicker bound layer will cause a smaller friction coefficient. How would that work? Okay, let's go back to the equations we had for boundary layers. Like this, and we are gonna assume the flow is always turbulent here. Right, that's the assumption. What is the equations we had for friction coefficient? Friction coefficient, that was like a number divided by Reynolds to the power. That's it, right? Exactly. So friction coefficient is inversely proportional to Reynolds number. What is the main difference between a supersonic flow and the subsonic flow when it comes to Reynolds number? So we are going to have higher velocity, which means that we are going to have higher Reynolds number, right? Which means you are going to get, it is inversely proportional to Reynolds number. So when you're going to get higher Reynolds number, then you're going to get a smaller friction drag, right? Because it is inversely proportional to Reynolds number. Higher Reynolds number, lower friction drag. But if you want to explain the physical phenomena behind it, is that you are essentially with higher Reynolds number, in general, you're going to get a thinner boundary layer, which means the viscous effects, which are the main driving factor behind the friction coefficient, are going to be less dominant in general. That's why you're going to get lower friction coefficient. So, but for your case, for this problem, the only thing you really need to do is to calculate the friction drag based on the turbulent conditions, and then it should be 20% less. 20% less for this case, which means that you just have to multiply it by 2.8. Why 2.8? 0.8. Yeah, 0.8 exactly. So it is 80% of your total friction drag in the laminar. Yes.
What is the real formula?
That's a very good question. The thing is, even for the laminar flow or for the whatever the friction drag that we are calculating for the subsonic flow, that formula is just an approximation. It is not the real formula. Yeah, dealing with, let me put it this way, Navier-Stokes equations or the governing equations, the main governing equations are unsolvable. And I don't want to say unsolvable, but they are impossible to solve, so which is the same thing in turbulence and laminar boundary layer things.
So why don't we have any pressure drag here?
Because we are assuming, what is the main reason behind the pressure drag? The flow separation, right? The adverse pressure gradient. We are just assuming that doesn't exist here. Okay. So how should we find the wave drag? So we only have wave drag and the friction drag. How should we find the wave drag? I forgot to give you these numbers. So rho infinity is going to be rho infinity. If you go to the table, rho infinity is going to be equal to 3.63 10 to the negative 4 slugs per cubic feet, and then T infinity is going to be 390 degrees Rankine. Mu infinity is going to be 2.86 10 to the negative 7 slug per feet second. Right? Yeah. And then using this, something that you need to know as well is the value of R in the British system, which is 1716. I don't remember the units myself now.
Gamma.
Gamma, what is gamma here? What is gamma of air? 1.4. Yep. You're dealing with air. That's the assumption. You're going to see a different gamma, two different gammas actually in your propulsion course. But it's because inside a jet, you're not going to be dealing with air. You're going to be dealing with a mixture of air and fuel, right? So your fluid is going to be different. We always assume gamma is 1.4 for air. Okay, so since we are getting to the end of the problem, I want to ask one of you to just explain to me how should you solve this problem. What are the equations you need to use? Huh? Okay.
You need to find the speed of sound.
Okay.
Then after you find that, you plug that into your model value equation to find the velocity. Then after you find the velocity, you need to run this number.
Yep.
And then once you find the Reynolds number, you find your coefficient of friction drag.
Mm-hmm.
And once you find your coefficient of friction drag, you can multiply that by Q infinite S to get dF of friction drag. If you need to find the wave drag, And once you find the wave drag, you add those two together. But with the wave drag, that equation is 4 alpha squared over square root of e infinite squared minus 1.
That's it.
Do the same thing with the q infinite s.
Okay, that's it.
So R is 287.
Oh no, R is 1716 for let me see, there are two questions, two online questions. I think the slope of the final wing is shallower. Looking forward to taking those courses. Which courses? Okay, we have two comments from Stephen and Emery. Emery says, I think the slope of the finite wing is going to be shallower, which I assume he means that it's going to be smaller, right? Right? That's shallower. Yeah. What was for the bonus point? Yeah, I know that was for the bonus point. So Nicholas and Emery will get the bonus. I'm not sure which course Steven is talking about. The Steven is the aero and lab. Okay. Oh, still you have not taken aerodynamics yet. Okay. Yeah. I'm looking forward to seeing you in that course.
I'm assuming the velocity we'll get is in meters per second, or would it be in?
No, it should be in you're doing. Let's see. I'm a little lost because I think concept may be bringing Imran that. Yeah, we can always meet. I can explain the concept to you over Teams or whatever. So, or you can always send me an email and ask questions. I have to monitor my laptop a little more. These poor guys ask questions and wait an hour for me to answer. Okay, guys. I guess you are all present, so you will get your attendance points. And we are out of time. And the next class, the students are so enthusiastic about the class that they gather around it. So let's just stop here. Pardon me? Yes, bring it. Please submit on Thursday. And we have to, I guess we are not going to finish this problem. But we are going to start doing equations of motion on Thursday. And that's it. Have a good rest of the day. Yes, please. Like you don't really need to send in the final answer, but you can if you want to. You will get the attendance point anyways. So I'm going to finish the live stream now. That's it.